I'm going to be talking to you about underwater explosions, and it can also be entitled How to Destroy a Submarine or a Ship. So this is stuff that I've sort of trawled out of my working life here, so I'll hopefully you'll find it of interest. So I thought I'd just tell you, I think many of you know who I am, but you might wonder, how the hell do I get into this stuff? Okay, so I'm actually a chemist by training. I got a PhD in chemistry from the University of Cape Town in South Africa, and I started out as an academic and then decided I wanted to get into the real world. So my first job was with a company called African Explosives and Chemical Industries, which was part of ICI. I think many of you know the big rich company ICI. So it was part of the ICI group, and I ended up in the research laboratory doing explosives, research into mining explosives. So it was still research work, but it wasn't academic work. In the 80s, I got an opportunity to join ICI's Group Technical Centre in IDEA, Scotland. And that was like ICI's central research lab where they were doing research into commercial explosives. So you're trying to understand the fundamentals, physics effectively, of how they work, how they actually interact with rock and break rock in quarries and in mines. And IDEA, Scotland, is actually a very, very famous place. It's on the west coast of Scotland, just down from Glasgow. Any of you are golfers may know Royal Troon on that same coastline. But IDEA was started by Alfred Nobel in 1871. So it was one of the many Nobel factories around the world. It was especially chosen for its bleakness and the rainfall population. And IDEA itself used to be massive. It was the biggest explosive factory in the world. During the days of the British Empire, all the explosives used in the mines around in the British Empire were made at IDEA and exported. It was also a munition factory in the First World War and the Second World War. Of course, it's pretty much defunct now. It's just a ruin. Most of the buildings are not in use anymore. I'll just flick to this picture. Those buildings were not built in the 1800s, but that was the IDEA Research Complex, and in that corner there, right in the corner, was the Fundamental Research Lab, where I worked there for 3 years in the mid-80s, which was a very fantastic experience. So I came to Australia in 1990, and I joined a company called Initiating Explosive Systems, which was a joint venture between ICI and an American company called Enzyme Bickford. And we were making detonators, things that initiate blasts. And this company built a new factory up in Queensland, near Toowoomba. So that's where I ended up first. And then I was transferred to Sydney. ICI became Orica in about the early 2000s. And the last project I worked on with Orica was an electronic blasting system. So actually computer control for blast initiation. And I was involved with a team to introduce the first such system to the Australian market. And I think I did give you a talk about this before on these electronic detonators. As what happens to many of us, I got made redundant because there was a downturn, and I just moved to Sydney, and I really didn't want to go somewhere else. And so since about 2000, I had a short time working for Sydney Water as an R&D manager in the government, and that was like probably my worst working experience. I mean, Sydney Water, the people are wonderful, the government interferes so much. So I didn't last there too long. And since 2006, I've been working as a self-employed explosive consultant. And I thought, who's going to employ me, because it's such a niche field, but of course there's been a mining boom and there's lots of companies that come into Australia and they need help with licensing and regulatory compliance and audits. And so my first job I got was for a company in South Australia who unfortunately had an accident and blew themselves up and sadly killed 3 people. And the government of South Australia said, you've got to get somebody in to come and help you get your systems going. So that's my first job. Well, they never actually were allowed to start up in South Australia. So guess where they ended up? In the Northern Territory. But that's a bit of the background to my working life. So as part of the work I was doing in the early days at AECI Explosives and also in Scotland, was measuring the energy output of explosives, and that is where this underwater testing comes in, and I'll talk to you about that. So I happened to sort of get out of university into the real world in a very exciting time for the explosive industry, because there were a lot of new products coming on the market. Remember, in the old days, mining explosives were the ones used in underground sticks of dynamite. And dynamite was a very dangerous product, killed a lot of people. And in the early 80s, a new product, emulsion explosives, came out. And these emulsion explosives are like, it's just, if you can imagine something like mayonnaise or Vaseline, it looks just like that. It's an emulsion, it's what's called a water in oil emulsion. And you might wonder what this is here, right? We used to make them in these Hobart mixers, which you'll go into catering places and they'll be making dough in that. Okay. So basically, you take ammonium nitrate solution and you mix it with some mineral oil and a surfactant, and you get this. And you emulsify it, and you get this stuff that looks just like Vaseline. But it's not explosives until you incorporate air bubbles in it, and then it sensitizes the product. Very, very simple, right? So what makes it hard for us to go and do that in the kitchen? This stuff. Ammonium nitrate, that's what bombs are made, terrorists use. It's so controlled in Australia. You've got to have literally an ASIO clearance to be allowed to have access to this stuff. So after 9/11, it was all locked down. So what was happening at that time, there were all these new explosives coming out, and you could literally dial up their performance. So you could literally you can change the formulation, you can change the density, and when I say dial up performance, it's the amount of energy that you could get out of it, right? And why that's important is if you're doing mining and you've got a very soft rock, you don't want too much energy going into it because you'll just shatter it. But if you have a very hard rock, then you need more punch to break that rock. So this was a fantastic new period. I should say, just a quick diversion, what's the difference between the military explosives and these ones I'm talking about, commercial explosives? Military explosives are all about shock and awe. So what you want to do is you want to shatter. You want to have as much shock into the target that you can get. So you want to break things, okay? With mining explosives, you want to break the rock to some extent, but you also want to push the rock away so that you can dig it out. And if you see movies of blasts, you see the explosive going off, and then this whole the rock in the quarry, the coal overburden moves. And so there's two things that happen with these explosives. There is the shock that goes out with the rock and breaks it up, and then there's gas that comes from the reaction product. So military explosives react very, very rapidly and quickly. Commercial explosives, you want to tone down the initial shock wave, and you want to get more gas out of it. And what we needed to do was work out how do we measure the performance of these new brews. And detonation codes, when I talk about detonation codes, there have been computer models developed to work out how much energy, how much shock you get out of the military explosives, because the physics upon which that is based is quite well defined. And a lot of this work was done in the Second World War during the Manhattan Project, because they used explosives to accelerate the uranium to get a critical mass to make it go off. So at that time, there were these computer models available, but they were based on military explosives. They couldn't correctly model effectively these commercial explosives, which tend to react a lot slower and over a long time span. So that's why we wanted to measure the energy output of explosives. So I'll just give you, just before we get into the underwater stuff, just to show you how do you actually measure the energy of an explosive. Well, really, something that's been around for a long time is what's called a ballistic mortar, right? So it's like a pendulum, and there's a very heavy container here, and what you do is you put a little sample of your explosives you want to test, and you set it off, and of course what happens is the little container goes one way, and this heavy bulb goes this way, and then you could, the height of the swing is a relative measure of how powerful your explosive is. So it's usually based, say, on something like TNT. So it's always measured in a relative sense, not in an absolute sense. And that thing's called a ballistic mortar. They are fantastic to do because this, the container that the explosive in goes that way at a hell of a rate, and we usually have a big mound of sand over there to stop it. We have to go dig it out to get it out. It makes a lot of noise and makes a lot of smoke. So you get to play with interesting toys. So that's right, that's really an old way of doing it. Another way that of doing it was this test, which was developed by a colleague of mine. I worked on this a lot. It's called a double pipe test. Right? So what we got is you got a hollow steel pipe, this water pipe, with an old steel pipe, and explosive inside that pipe, looking at it from the end. So if this is the setup, so this is a heavy steel bar, and that's what we call the witness pipe. Okay? And that's the pipe containing the explosive. And this, the top pipe, sort of 38 millimeters in diameter. You put sticks of explosive in there like you do in a borehole, and then you set it off. Okay? What happens is the top pipe completely shatters, but it compresses this bottom pipe. And then you could measure the deformation of that pipe as a measure of how that explosive is performed. So you're trying to simulate what happens in a real borehole in rock. And then so results look like this. Okay, so what you do is you measure the pipe depth in millimeters. You go along the pipe, along the length of the pipe. And then you can see, they all sort of start at the initial diameter of the pipe, and then the dent increases. Now what's happening with this one is the explosives in that pipe are actually dying off. See, they go off, and then the dent goes to zero. So the explosion is not actually propagating all around on the pipe. So I won't go into the technical details, but it's a very useful test to show that effectively what was happening in this test, because there's an air gap, you notice back here, let me show you. See, there's an air gap here? So what happens when that explosive is going off down the pipe, the shock wave from the explosive is running ahead of the reaction in the stick of explosives. So it's actually squeezing the hell out of the explosives ahead of the reaction point. And it's actually dead pressing it, we call it. It's actually killing it. The density's going way up, and when the density gets too high, it won't go off. So the reason we did this was because they were putting these products in the mine, and people were finding undetonated explosive in the borehole. They were drilling into it and really killing it. Right? Not good stuff. So I said, what is going on? So that's why this test was quite useful to kind of understand, and then they reformulate and do various things. So so look, can I tell you that when you're setting off one of these, right? So there's 3 meter long pipe. You've got up to 4 or 5 kilograms of explosive in there. You're going to set it off. We had to go underground into a bunker, and we set off because all of the steel used to fly around. It's like It's like being under water attack. You hear it coming down your head. Interestingly, we always found this piece. This is the piece that's in contact with the bottom pipe. We would always find this, what we call the contact strip. It's where the top pipe met the bottom pipe. So they were quite, and we chromed them, and they were sort of tended to decoration. Any questions?
Lots.
Lots, okay. So let's get into the good stuff. So one of the tests we did was what we call the underwater explosive test. And the underwater test was developed to measure the energy output of these new emulsion formulations. So this could actually measure the actual energy output. And it was designed to sort of try and predict how these things would work in the field, in other words, in the mine. And we were trying to understand the split, because when the explosives go off, as I said, they put a big shock wave which cracks things, and then there's this gas that comes on behind. And if you can find that gas, it can actually move things. So we wanted to understand what was the split between the gas energy, or heave energy as we call it, and the shock energy. Now, military explosives don't care about the gas. All they're interested in is shock. Yeah? We want to break things. So, and we were looking at, changes in formulation. We added aluminium powder to these explosives. We add solid ammonium nitrate to see how all of these things react and how they affect the performance. So, and so this underwater test is relatively easy to set up. I'll show you in a minute. And you can do quite nice big samples, like a kilogram of explosives, where a ballistic mortar can only do 10 grams. So you can do it on a larger scale. So that's why this test was developed. Now, the science behind this underwater testing and how and the equations there and how it all works came really from work that was done by the military, mainly in the Second World War, and it was all about understanding. It was work on depth charges and torpedoes, and how to destroy submarines, and in fact ships as well. If you put it under the keel, I'll show you a great video of that. So the Americans did a lot of work on this, and the British as well. And what happened is a lot of these scientific reports were declassified in the mid-70s. So this information became available, and hence the idea came, well, maybe we can use this underwater testing. If we measure the output underwater, and I'll show you how that's done, it'll give us useful information on commercial explosives. So that's where that comes. It all comes from the military. So I'm going to show you a little video. Hopefully this works. And for some weird reason, it starts quite a long way in. So I'm just going to go back here. So.
Here, number 8,
Sorry, not yet. Okay, so this is a video from 1947, declassified. Hopefully you can hear the sound. Sounds good?
This diagram shows the action of a small-scale underwater explosion. At the instant of detonation, an enormous initial pressure, estimated to be in the order of 100,000 atmospheres, is produced. This pressure dispatches a shock wave and imparts a large momentum to the water. Because of the large momentum, a gas globe, produced by products of the explosion, expands radially outward. It travels beyond the point at which its internal pressure equals the hydrostatic head of the surrounding water. Eventually, however, the hydrostatic pressure brings the expansion to a halt. And since the interior of the globe is at a low pressure, a contraction is started. At the point of collapse, another shock wave will be sent on its way, and the cycle of expansion and contraction will be repeated until all the energy of motion is dissipated.
Just stop it there. So that's what happens when you set off an explosive underwater. You get the initial shock wave that goes out, and you get this bubble, oscillating bubble that is, of course, it's moving all the way to the surface. So just
How much of that will happen before the shockwave hits the surface?
no, the shock wave, no. Well, it depends on the depth. But
Yeah.
generally, the shock wave will reach the surface well before the bubble.
Total depth of the water is 6 feet. Note that each succeeding pulse decreases in amplitude and duration.
I want to go this way. Right, so this is a schematic of what happens when you set off. So the explosive charge goes off, and then if you have a transducer in the water, you'll see this initial pressure pulse, the shock pulse from the initial detonation, and then you'll see a series of these pulses when that bubble is collapsed and it's about to expand again. There's a number of these, okay? Now, what happens when we do underwater testing, how this works for commercial explosives, what we do is we measure the time of this first bubble pulse, and that can be used to then calculate the energy in the gas from the explosive. So that's effectively the gas energy. So if we have a pressure transducer, we can measure actually the shock energy, and then from the time of the first bubble pulse, you can measure the gas energy. So that's why it's used.
That'll vary depending on the depth, I assume.
Absolutely, there's lots of complications, Clifford. Yes, I'll talk about that. But so, I mean, so just to explain as I'll talk again, this was really designed, and these bubbles actually are what kills submarines, right?
Mm.
Not so much the shock, and I will show that. But based on that understanding of the science, and there are some equations later, in commercial explosives we use the time from initiation to the first pulse to get a reasonably accurate estimate of the energy in the explosive. So for a 1 kilogram charge, you get, the energies are of the order of 3.5 to 4 megajoules. So they put out a lot of energy very quickly. Short time, a lot of energy. So, so there's two things that we measure. This is the so-called shock energy, which you measure using a pressure transducer, and what we call the bubble energy, which is the work done in expanding the gas bubble. And those two, the shock energy kind is an estimate of the ability of the explosive to break the rock, whereas the bubble energy is an estimate of the ability of the explosive to move the rock or heave it. This energy here, shock energy is, I don't know if you've heard the term brisance, which is a French word for kind of what military explosives do. They want to break things. They want to destroy things. What we want to do is we want to balance these two effectively energies, and they come out on a different time scale. This one's pretty quick, this is much slower. And that, to be honest, when you see a mine shot going off, this is the stuff. The gas energy is what actually moves the rock into a nice pile that you can dig. So that's why we did. So that's why we, wanted to do that. So how was it done practically in South Africa? We had a purpose-built, we used to call it the pond. So it was actually blasted out of rock. There was a gantry and a control room, and the charge was suspended off the end. And we press the button and we measure and do all these tests on the different formulations. I should say, one of the technicians she forgot to put it in the water. So she blew the end off that. She was pommy, mind you. So that, in fact, this facility in South Africa was probably the only dedicated one in the world. You know. At that time, that was the biggest explosive factory in the world, so they could afford to do that. Most other people do it in a disused quarry. Something like this. So if you want to know what it looks like when you're not blowing ships up, that's it. So you don't want it too shallow. Oop. I'll run it again. It's a lovely, peaceful, sunny day in the US. This is actually the US, right? This is actually a commercial outfit that do this work. If you've got a product, I'll test it for you. So here's some, this is what, so remember these are scans from the 1980s, by the way. This is from a report. But this is what the pressure profiles look like. So this is the pressure, what the pressure transducer, that's the shock. You integrate that to get the energy, and these are the pulses. And if you put a hydrophone in the water, just to listen, this is what the different bubble pulses look like. And you can see the the time scales on the millisecond time scale there. So that's what the output looks like of these tests when you do a commercial. I can see your brain ticking over there, Clifford.
I'm thinking it's going to be very different in the rock. But
So of course, as Clifford said, there are many issues with these tests. One of the issues is the depth of the pond, because what happens is that if the walls of a pond are too close to the explosive, you get what we call, there's reflection from the side walls, particularly from the shock, but also the surfaces tend to attract the bubble and distort the bubble. And so there's a lot of rule of thumb that the depth that you've got to put it in is about 2/3 the depth of the pond or the quarry you're using. The other thing is the shape of the charge, and we'll see this in a minute. So spherical charges work best. Long, thin charges you have to correct for the length to diameter ratio. And generally, and I did a lot of work on this, generally you calibrate the pond and the equipment to understand the wall effects using spherical charges of pentalite or TNT. So pentalite is a mixture of high explosives called PTN and TNT. So we used to make these bombs, spherical bombs, and we used to calibrate the pond using those charges. So it's fine if you live in a country like Australia. RCI in Melbourne had a quarry in Epping in Melbourne. Different, you know where that is, Epping. In South Africa, well, the weather's here, but doing this work in Scotland was bloody bleak and miserable, I can tell you, because it gets very cold. I'll show you some pictures of. So that was our setup back then. This is what the instrumentation looked like. All analog. Oscilloscopes. This was the control room, and there were a series of pulleys that would pull the charge out over the quarry, just use the quarry and then lower it into the water.
how far away would this explosion be picked up on a seismometer?
A good question. I mean, they're only kilogram, but they probably would be, yeah. Hadn't thought of that. Yeah. Because the water does dampen it a lot, of course. And that's what we that's that's what we played with. That's actual some photographs of our tests we did. That's what the collie looked like. There's the control room, and so if you look at the plume, you can see this one is not as symmetrical as that one, so that could be related to the shape of the charge we applied. But yeah, we did have a lot of fun actually blowing things up, trying different things. And so these are some results. I mean, unfortunately, they're all relative, but it sort of, this one sort of, all of these things are measured. This is relative weight strength, which is the power of explosives in the bubble test. And for ammonium nitrate fuel oil explosive is like the standard, and everything's compared to that. So it's sort of showing you how the energy changes with changes in density and so on. This one is showing how the energy changes from an oxygen positive to an oxygen negative. What it means is that generally the explosives have what's called an oxygen balance, and that's making sure that the oxygen available through the oxidizer, ammonium nitrate, balances what the fuel needs for 100% combustion, and so if it's off, the energy drops. So if you've got too much oxidizer, the energy falls off faster than if you've got too much fuel. That's what that's saying. So these are all insights that we gain by doing all these kinds of tests. So these things, we knew theoretically what should happen, but this is actual ability to test it. So before I get into submarines, so this test, this testing is actually largely no longer done. The main reason for that is that places to do it disappeared, like that South African pond was closed down. The factory sort of changes now nature reserve. Orica can't get its Epping pond, probably houses there now, and so the only way you can actually do this is with an external contractor, and you have to go to the US for that. So, but the main thing though that has changed it is that the scientific understanding of how these non-military or commercial explosives work has advanced in leaps and bounds. So you can do, the modelling actually has replaced a lot of this testing.
But you have to do the testing to work out how to build the models.
Yeah, yeah. But they have other ways of calibrating those models now on a smaller scale. You can do little testing drums and things. So I said the other thing I would say is that the science of these explosives has matured, and there's not much more we do. Unless something new comes along, we sort of understand mostly how it works, and the companies involved don't want to invest any more certain dollars in this. They're looking at other things. So the whole science of explosives has moved away from the chemistry side to much more the engineering side and automation and electronics. So it's all shifted. The main testing that's done still today is looking at the shock impacts on electronic systems, because they're embedding whole. They used to connect things to glass together with wires. Now they're wireless, and they've got wireless like computers effectively down each glass tile, which they communicate wirelessly with them. So that's where all and these things shaken up in the glass break, and electronics gets cracked. This is their challenge at the moment. Right. So that's the background to that. Any questions at this stage?
I've got a question. What's the use of that in the army?
I'll tell you about that. Yeah.
What's the main use of, besides illegal fishing, what is the main use of commercial underwater explosives? What do they use it for?
Well, so Rob, this was we sent them off underwater because we could measure the energy that way.
So that's just for
that's
testing.
all it's about.
Oh, okay,
yeah.
Right. So there's no commercial use for it.
Well, I mean, unless you want to blast You know, they do underground blasting when they want to dig out some rock and
underwater
and so on. But
they want to make another panel.
Yeah.
Canal
But look,
thing.
all of this stuff, what I'm talking about now, is where it all came from. Right? So we just piggybacked on and said, oh, we can use the science effectively that was developed
Yes.
by the military to measure energy of explosives.
Yeah.
So it was.
It's more a testing regime.
It's a testing regime.
Yeah.
Yeah, that's exactly right. Yeah. I was talking about Semtex. Semtex is a plastic explosive. So what they have, so it's a high explosive, or a secondary explosive that's in some sort of matrix, some sort of polymer matrix that you can bend, and you can, you know, if you want to blow a door, you can put it around the outside and blow the door out.
When I was in the army, we put it on trees.
Yeah, you can make it.
About that diameter.
It's like plasticine, isn't it? Yeah, exactly. Yeah, that's exactly what it is. Yeah. So, I suppose the interesting thing about this is that when we look at this now, this all came from the research that was done, you know, in the war, probably before the war, about how a depth charge could destroy a ship or a submarine, right? So, and interestingly enough, that if a depth charge goes off or close to a submarine hull, you get the shock wave that goes through the water, impacts the hull, and it'll shake it up, right? Might break things, but the thing that really causes the damage to the submarine is actually that oscillating bubble, because there's a huge amount of water that's moving. And somebody described it to me as, imagine what that bubble does. It effectively, it's like taking a toothbrush and going backwards and forwards like that. Eventually it's going to break. And the movement of that water flexes the hull or the structure to such an extent that can actually destroy it. And so the bubble, and I'll show you some videos in a minute, the bubble is what does the damage. Most submarines can, if the depth charge, that means the depth charge has got to be the right distance from the hull. So that water can, because that bubble, as it's oscillating and there's a lot of movement there, is actually attracted to a surface. It moves towards the surface. So if the hull's close enough, it'll move towards the surface and effectively start this flexing action, which can destroy the submarine. But that's how you destroy a submarine. It's not the shock that does it underwater. It's actually the oscillating bubble.
Is that also to do with the duration? Because the shock's much shorter duration.
The shock is much shorter, correct? Yeah. Perfect, exactly right. The shock comes through very fast. It might break things, it might, you know, destroy
So you've got water outside, air inside, so the impedance...
Yeah, you get a bit of reverberation inside and so on. But that bubble, so you sort of do some initial damage, you might create some cracking or whatever, and then this bubble comes along and this flexing thing happens. And that's what destroys the submarine. So, this is how to do it. So this video goes for about, it's not too long.
Hi, I'm Mark. And I'm Adam. And we're interested in exploring the phenomenon of underwater explosions, specifically how a torpedo sinks a ship.
Contrary to popular belief, water torpedoes do not actually have direct impact with the hull of the ship. Instead, they use a proximity fuse to detonate beneath the ship. This detonation vaporizes the water around the torpedo and creates a high-pressure, high-temperature steam bubble, as well as an intense shock wave beneath the keel.
When the detonation occurs below the keel, the resulting pressure wave of the explosion lifts the ship, weakening its keel in the process. As the steam bubble collapses, the ship is sucked down by negative pressure and appears to momentarily sag in the middle. When the steam bubble finally reaches the surface, it explodes through the hull of the ship as the change in pressure creates another more powerful shock wave. This combined effect often breaks smaller targets in half and can severely disable larger vessels.
We attempted to recreate this phenomenon on a small scale by creating a high-pressure air bubble using an air pump in a small balloon. By inflating the balloon until failure, we simulated the rapid expansion and subsequent collapse of the steam bubble created by the explosion.
You can see the shock waves on the surface created by the initial popping of the balloon, as well as the oscillations of the bubble. These oscillations occur as the internal pressure of the bubble approaches the hydrostatic pressure of the water surrounding it. Once the internal pressure reaches the hydrostatic pressure, the bubble begins to contract.
This phenomenon results in a rising, pulsating bubble, expanding and then compressing, emitting pressure waves into the surrounding water column. This is known as isotropic propagation. Despite the relatively small bubble, the shock waves generated from these oscillations can cause tremendous damage to nearby solid bodies due to water's incompressibility.
The bubble's behavior is governed by the Rayleigh-Plessis equation, which is a unique derivation of the Navier-Stokes equation. In its general form, which is unsolvable, the equation shows the relationship between the internal pressure of the bubble, the external pressure, and the radius of the bubble.
Because the Rayleigh-Plessis assumes a spherical bubble and a constant internal pressure, we cannot completely calculate the exact behavior of our bubble. It does allow us to see how the changing radius over time induces a difference in pressure in the surrounding environment. As the radius approaches zero, the pressure difference must go to infinity, creating those deadly shock waves on the surface.
That's quite a good one, that. Okay.
Hi, I'm Mark.
Oh.
And I'm Matt.
Right, so, of course, these underwater explosions were taken to their extreme in nuclear testing. So that's a photograph of Bikini Island, 1945, where they set off a nuclear bomb underwater, and at a 23 kiloton TNT equivalent.
Just a baby.
Just a baby. So I've got a video now. It's a little bit longer. It's a bit historical, but it shows what happened. And this is for you, Colin, because this is how you destroy a whole navy. Mate.
I think they also made a mistake with Bikini when they thought it was going to be 15.
Sorry, what was that, Ron?
I think they made a mistake. The Americans actually made a mistake. They thought it was going to be 10 or 15 kiloton explosion, but they hadn't factored in something other, which ended up being a 23 kiloton
Yeah,
explosion.
and this is, I think this is one of the fourth or fifth bomb that they set off, so it's pretty early days. But
Well, quite a few ships in the water around it too.
yeah, look, I found this video. I think it goes for. I think it's worth watching.
7 ships take positions 3 miles off Bikini to suffer the shattering impact of the 5th atomic bomb.
Fifth atomic bomb.
Here will be tested the capacity of modern armament to withstand the crushing shock of compressed water traveling a mile per second. The evacuated ruler of Bikini, King Judah, gets a front row seat at the bomb blast as he arrives aboard the Mount McKinley and is greeted by Admiral Blandy, Joint Task Force 1 Commander.
So too unhappy with them being blown up.
The bomb raft for Test Baker is ready. The abandoned ship signal is hoisted, and the scientific staff and crew are checked off. Last man off the deadly weapon carrier is Admiral Parsons, who set the switch for the blow-off. These historic pictures are the result of the joint efforts of Army, Navy, Marine, Air Force, Coast Guard, and newsreel cameramen. It's a graphic record of one of the most terrifying happenings in world events.
Summertime. It's very super hot.
Admiral Parsons, Navy's #1 atomic bomb expert, reports to Admiral Blandy aboard the flagship that all is in readiness for the test. Close by, the Los Alamos firing ship receives the staff of scientific personnel, which will time the experiment and set off the blast by radio beam. These are the instruments that will loose the bomb on the test area. Striking just below the surface, the nuclear release smashes at 5 times the speed in the compressed water as it would in the air. The signal, 2 minutes to go, and everyone in the fleet stands by to picture history in the making. A scene that excites even the most experienced newsmen. Throughout the observant fleet, all eyes are trained on the blast point. Seconds, 20 seconds, 15 seconds, Dr. Holloway, leader of the Los Alamos group, and the entire fleet wait in almost agonized tenseness. Now about 5 seconds to go, and... The awful roar of the blast, equal to a discharge of 60,000 depth charges, each weighing 600 pounds, strikes the ears of the observers. Many miles away, the raging might of searing flame, crushing force, and deadly radioactive water is seen falling in a killing mist, as the great circular wall of sea closes in on the guinea pig fleet. The combined forces let loose, swamp the nearby ships, and crush their thickly armored hulls like cardboard. Seen from the air, the towering waves set in motion appear to be only shallow ripples. The beach at Bikini gets a pounding. A television screen records an on-the-spot picture story. Drone planes fly through the turbulent air mass above Bikini Lagoon, deadly with its radioactive gases. And for days it was not safe for salvage crews to board the damaged ships. Geiger counters recorded the intense rays, which would have proved fatal if the ships had been manned. When task force observers under Admiral Blandy made the final tally of ships sunk or damaged, they found the Jap battleship Nagato badly damaged. She later sank. The destroyer Hughes was beached to prevent its sinking. 5 submarines were listed as sunk or damaged. And the historic old battleship New York was a battered hull, its superstructure twisted and torn. The proud Saratoga, veteran of many naval campaigns, goes down many hours after the blast. Efforts were made to salvage the historic carrier the Japs could never sink, but old Sarah finally goes down in the cause of science. And now are shown the most dramatic pictures of the underwater blast. Here is the motion picture spectacle of all time. A million tons of water, alive with deadly rays. Awe-inspiring in its significance for man, who learned how to control the atom, but must now learn to control himself. There is but one defense against the atom bomb, and that is distance. And distance will mean nothing without world peace. This is Crossroads.
That's it, fellas.
Hey.
Just a question, Mike. You said that the testing ended because they lost access to their dams,
The
ponds.
dams, ponds, yeah, quarries, yeah.
But surely, you know, places like Leonora in West Australia, there's dozens and dozens of abandoned huge pits there, which are all full of water. So if they wanted to do testing out there, surely they could do it.
Yes, they could. But I think the reality is that they feel they don't need to do it anymore because this particular generation of explosives they understand sufficiently to kind of do everything they need to do. So the science has matured, or the technology has matured, and we haven't seen anything new coming along.
So is there anything on the horizon, or is this it, do you think?
Now I think so. The explosives, puts the energy into the rock effectively. What's happening now? It's all about electronics and the timing and the sequencing of things, and also the computer modeling. So you can actually, the model will tell you exactly how much energy you need, and you can dial up the product to fit. So it's sort of moved into modeling, into electronics systems and electronic timing. So that's where the technology is, and it's it's sort of moved from, let's say, chemistry and physics into engineering. So there's a lot of work going on with automation, with equipment, with drill rigs, GPS, all that stuff. So getting people out, just doing it from a control room. So it's really now an engineering challenge rather than a scientific challenge. So, yeah.
Mike, you talk about setting things off electronic radio signals, or
yes.
how compatible are they with other systems? I ask this because when I lived in Jersey, we were busy setting up a VHF UHF contest site, and they're doing some blasting nearby. And we were just a bit concerned that when we started transmitting, we were going to set off these radio things when they weren't ready.
Yeah. So if you go and look in the Australian standard, which is based on the Second World War, there's a whole lot of stuff there about the use of radios and transmitting devices near electric detonators, which are just basically two wires and a little matchette. And if you get an EMF induced, it will warm up the wire and bang will go. There's new electronic systems that have got all these fancy systems in them to make them immune to EMF, basically, and high-powered radio and power lines and all the rest of it. That being said, there was a case recently where something went off and they're still investigating it. So they're supposed to have worked it all out. I don't understand it all. But as you see, before they used to have wires coming out the hole to an electronic module. Now they've got, it looks like it's a plastic tube, it's got batteries in it, it's got radio, wireless in it, and it's wireless communication.
All remote control.
All remote control, yeah. So that's what, that's the current state of development.
Ruby.
I'll come to you,
Mike,
Russell.
if you were blowing the side of a quarry in,
yes.
do they put the charge in some kind of a canister that makes the force of the charge go in one direction?
No,
or is it 360 degrees?
They just drill a hole in the rock, right? They fill it with explosives. But what the timing, the shock or the braking effect will go in all directions. But they time it so the front row of holes go first. So it's like cutting a cake. You slice off the first bit and blow it, and then you blow the next row, and then the next row, and so on. So that's the timing. So it's so quick. It looks like it's all happening.
You said it in the video.
Yeah. So it's like rows and rows.
It's sequenced.
Yeah, it's sequenced, and it's all in a millisecond timing range. But the trouble is, though, so you've got all these holes. So you can imagine, like a bench, and you're blasting. You blow the first lot of holes. All those holes behind they're waiting their turn are getting shock waves coming through the rock from the ones going off before. So this is where the damage to the electronic modules, the damage to the explosives is happening.
Okay. That's the issue.
That's the issue. Yeah. So timing is absolutely everything. Timing is becoming more and more critical, particularly in quarries, because a lot of quarries these days are very close to population centres. And when explosives go off, they create a lot of noise and vibration and shake houses. So the electronic modules allow you to tune the blast to minimise the vibration. And also in underground mines where you don't want to bring the whole roof down. So, yeah.
So what would be the maximum number of charges that you'd let off?
Well, if you imagine one of those big coal shots, and they've each got 450mm holes, 10 metres high, 1,600 holes.
Wow.
Those are the ones they've registered on the seismic gauges.
1,600.
Yeah. I mean, up in the Hunter Valley or in Queensland, these coal shots, they take weeks and weeks to drill it and load it. It just sits there. And then they set it off and it'll be gone within a few seconds.
Okay. And it's, this is
So,
the strength, the
so,
sequence, the time.
Yeah. So the thing about the explosive industry which I was involved in, it really is a fascinating industry in the sense that there's a lot of science, there's a lot of technology, and it's still evolving. And Australia is actually really at the forefront of that.
We're digging up Australia.
Yeah, there's a lot of science going to digging it all up. Yeah. Yeah.
Oh, nice.
Yeah. Clifford, sorry.
I was going to ask a question, but I've got a quick anecdote first. My grandmother retired to Point Lonsdale on one of the reefs, on a hill that was a limestone reef that was one of the reefs that partially blocks the entry to Port Phillip Bay. And they used to blast to make the channel bigger, like bigger ships in. And they had a lot of pictures in the house, and she had to go around and straighten the pictures after every shot.
Yeah.
But what I was going to ask was explosive forming. There was explosive forming of metals into things like rocket nose cones or yachts' hulls and things. Is that still being done?
Yeah, that's still being done. There is a company in Sydney actually who they're based at Fox Studios down there.
Oh, right.
And they started out doing special effects for the movies, and they do all sorts of explosive forming. They also do lots of things like cutting, old drill rigs, ocean-based drill rigs or oil platforms.
So that'd be relying on all the results from your research, I assume, with them.
Yeah.
Well, there's a lot of knowledge about how to cut things off from the military. Yeah.
That's great.
Yeah. And there's another very interesting product that in some underground mines they have these, they call them ore passes. So when you blast at an upper level, then they push the ore down effectively a big chute that goes to the bottom of the mine, and then it gets taken out on a conveyor. And sometimes they get big rocks locking up in these ore passes and they jam. And then they've got this thing called a ballistic disc, which is like a shaped charge, which is a semi-military thing, like a tank. Tank weapons have it in. You shoot it at the rock to dislodge it. It's also a piece of fun equipment to play with.
I remember that being discussed in underground copper mines.
Exactly.
From the Power of One, I think it was, or one of his books.
Oh yes, that's exactly right.
Yeah.
Yes, correct. Yeah.
Megalithous mines.
Great. So, any other questions? Thank you very much.
Very well.
Very well.